All right, Stefan, take it away. Thank you so much again.
All right, no problem. Thank you. Okay, so this is a two-part tutorial on dynamical low-rank approximations. I was asked to do this due to some interest in this over the other mimics using this technique. So I think it's best for sparse 2 to know what it is and how it's useful and where we can kind of contribute to it. So during this, if you have a question, feel free to raise your hand or speak out. If you don't understand something, I want to make sure we're all clear on things before continuing. This it's a pretty new technique, so there's not a lot of information on it. So I try to list the appropriate sources where available as well. Okay, so this portion is just going to cover the theory of dynamical low-rank approximations, not actually how it's used. The reason for it is because there's kind of a distinct gap between the theory and how it's actually applied through some of the integrator techniques. And we'll get to why that is in a bit. But this section is focused on the theory, the theoretical results, an illustrating example, and kind of why there's a break in how we actually use it versus how it's formulated. And next time we'll talk about the actual techniques people have developed to apply this dynamical low-rank approximation to actual problems. Okay, so this the framework of this is trying to evolve a time-dependent dynamical system with matrix-valued solutions. So we're going to have an ODE, y prime equals f of y, where y of t right here is a matrix-valued function dependent on time. We're going to assume that the ODE f is autonomous, but all this applies to where you have sources or if f is a function of time as well. And the goal is to be able to compress the solution y throughout all time. We do not want to keep the m by n matrix full in memory. We want to be able to have some compression that we can use instead, some approximation at specific time points. To that end, let m sub r, the script m sub r, be a subset of the m by n matrices, be the manifold of rank R matrices. And the goal here is to find an approximation matrix U, that's rank R, for all time positive that sufficiently approximates the solution Y for all time. And since U is low rank, we can then decompose that U as a C times S times D transpose. This is a notation I'll use throughout the talk, where C and D are orthogonal matrices of size m by R and n by R respectively, and S is given by some non-singular matrix. So the classical way you can think about this is we're trying to take an SVD truncation, rank R truncation at every time step that I care about.
Sorry, can I ask already, how should I be thinking of M and N?
So in terms of this talk, there's going to be generic parameters. In terms of the context of problems, it's just the problem size of what you want to develop. So in the context of like kinetic type problems, which we saw at the mimics meeting, M and N are some discretization parameters, which are usually very large.
But I guess, sorry, so you're turning N into R. So for N, you're using lower rank approximation. So I should be thinking of M like the grid cells or something, and N is
yeah. So M and N are the grid cells in 2 dimensions, and then we're trying.
I see. Okay.
All right.
Thanks.
No problem. Okay, so there are 2 kind of
related question. So M is not it should be the number of grid cells, right?
Correct. So for example, this is like a 20 by 30 matrix right here. So M is 20 and N is 30, and this is a rank 4 decomposition here. Yep.
Yeah, but M, in 2-dimensional, M will be a square of something. In 3-dimensional, M will be
higher tensor. So we'll get to the tensor. No, we'll get to the tensor notion later, but for now, we're just going to consider matrix 3 for currently.
Right.
One more question, sorry. How do I think about the dependence on T? Or should I think about each time step being totally independent from the others?
Exactly, yes. So, I mean, there is some continuity by the equation, but there is no dependence between any specific time on the matrices right here. Exactly.
Okay.
So each of these factors are a function of time themselves. So the matrices, the C, not just the coefficients S that glue them together, but the basis matrices will be different in time as well. That's a unique characteristic of these methods. Okay, and again, questions are welcome. So there kind of been two main techniques to try to evolve these approximations in time. The first one is what's called, it's kind of the earlier one. It's called step truncation, and it's in the name. The goal is to step forward your ODE sometime and then take a truncation of that, and that can be done through an SVD or some other randomized process. So if your low rank manifold is given by this blue patch right here, and you're some time step UK. The goal with step truncation is to evolve the dynamics of the ODE. That will probably take you off of the low rank manifold, and then after some sufficient time, you project back on through some SVD truncation and continue. So step truncate, step truncate. The advantage is you know what you're throwing away. The SVD is very robust in that sense, but it can be slow, and you do require the full matrix Y when you take the truncation. Right now, there are some, depending on your problem, there are some ways to bypass these details, but fundamentally, this is what you're doing, is some sort of SCPD truncation at every step. What dynamical low rank approximation does, in a general sense, is it evolves the dynamics of your model F on the manifold itself. So you can think of it as this red line right here. So at no point during the simulation do I leave the manifold. I'm going to continuously evolve the dynamics on that manifold and never leave it. And you will end up probably something different than step truncation. To do this, we first truncate the initial condition to some rank R approximation, and then evolve the coefficients C, S, and D. And it's going to be in some nonlinear system of the components as well. The advantage of this is you have some quasi-optimal approximation, at least in short time, compared to the SVD truncation. So you're going to be some constant away from the SVD truncation error to your true solution. But there are several disadvantages as well. And I don't want to talk about how this is the greatest method in the world, and there's nothing wrong with it. There are some issues. Do you need a specific structure of the ODE in order to evaluate these quickly? We'll get more into that next time. The theory is not as advanced. A lot of these techniques derived are explicit in first order. No fancy time integration techniques or much to speak of. And the nonlinear, the manifold gives you nonlinear dynamics, which can be pretty messy. An advantage of this, though, or I guess a difference between this and other, you could classify dynamical low rank as a reduced order model, in the sense that I'm trying to take some full order system and reduce the complexity of it to some specified basis. But unlike reduced order models like POD, proper orthogonal decomposition, what they do is they take snapshots and configuration and time space over multiple types of simulations and take a giant SVD offline to create some optimal space-time basis, which then you use as your reduced order model as you for the problems that you want to test. So you have this massive offline step, and then you have this much quicker online step for stuff like POD. Dynamical low rank, on the other hand, is always online, in that the basis functions C and D, depend on time, and they depend on the dynamics of your operator and the current position. So the basis for your reduced model is constantly changing in time, which is good because you don't have to do this huge offline step and worry about configuration spaces you might not even touch, right? But you do introduce some different dynamics to the system. So dynamical low rank, at least in my experience, has been applied to several applications. This is not an exhaustive list. As we saw at what CharmNet is doing at the MXPI meeting, this is very popular for kinetic equations. And the goal here is to reduce the recursive dimensionality when not dealing with 6-dimensional type problems. I'll get into a little bit of that in a second. There's a lot of references on dynamic low rank being applied to kinetic problems, but if you want to look into any, I recommend looking into Lucas Einkemmer from Innsbruck. He's done a lot of work in dynamic low rank for kinetic type problems. And you can also look up Ryan McLaren from Notre Dame, and he recently just had a student graduate, Peng, that did a lot of sweeping discrete ordinates with dynamical low rank. But just some other things too. I've seen problems with hyperbolic problems, UQ with uncertainty. You can look at this paper by Jonas Kusch, who's at Oslo right now, and Asserti at EPFL. And also, this has also been done with neural networks as well. So this is a pretty interesting case. So you can think of the minimization of the loss function of the neural network as a gradient flow to the minimum. And essentially they used a low rank decomposition for the weights of a dense neural network and applied dynamic low rank to it and got some pretty interesting results. So the techniques, the uses for this are pretty widespread for matrix compression. I'm a PDE guy. I'm trained in class or discretizations to partial differential equations. So I kind of want to relate it back to that context a bit. So in the context of PDE, suppose, and I'm going to talk about specifically kinetic problems. Suppose you have a distribution F, which just depends on physical space X, velocity or momentum space V, and time. And I want to essentially discretize this in some basis, discrete basis in space and velocity. Then I can represent it as this huge giant matrix distribution, where Y is what I had before, and X phi is each basis function in X, and psi is each basis function in V. And in a 6D problem, both M and N are essentially order N cubed, where N is the number of degrees of freedom in one dimension. So if you were to try to do this in a true sense, without any low rank techniques, you're looking at an into the 6 type of problem. So very, very large, terabytes of memory to store this. And again, it doesn't matter the actual basis. Yes.
So why is your basis not time dependent anymore?
The base, so this is, can I postpone that for a minute?
Okay, fine.
Okay, yes. No, you've called us something new. This is exactly right. The basis discretization doesn't matter, but in this case, in this model, the basis is some fine resolution detail that you've hoped to essentially assume is ground truth. And these here right here. So we're talking about very fine level grid cells here. And what this low rank dynamic low rank decomposition is actually doing is it's actually taking your basis, your coefficient matrix Y, and it is splitting this up in this low rank decomposition. And if you plug that ansatz into the approximation for F, you can then do some algebra, you can do some associative and group phi and C and psi and D, and you can kind of create low rank spatially dependent and velocity dependent basis functions X and D. So what dynamical low rank approximation is actually doing is actually picking the best linear combinations of discrete basis functions to give you the best representation in a low rank space. So it's kind of picking and choosing which low rank functions which basis functions you actually need to represent the solution instead of having to represent all of them as linear combinations of all of them. Does that answer your question, Sherry?
Yes, so that's good, but I guess after the tutorial, I will have a better understanding why it's you can do this.
Sure.
You can do, yeah. Okay, go ahead. Yeah.
So the way to think about it is if you had some I'm getting kinetics, but if you had some Gaussian distribution, right, it's an exponential in X times an exponential in Y. Instead of trying to represent the full phase space and trying to pick out e to the X plus Y at every single grid point, you can think of it as it's picking out e to the X times e to the Y and then multiplying them together.
Yeah.
And the idea of this, there isn't there are several competing ways to try to compress these solutions. Sparse grids is another one that I also work on as well. And people are using neural networks for kinetic problems. There's no leader yet. This isn't a fleshed out field. This is a very currently researched topic of which one of these techniques is the best. But the hope and the idea is that the kinetic distribution, the dependence on the rank is kind of decoupled from these discretization parameters. So I can take these discretization parameters extremely fine, and hopefully the rank doesn't grow too much. And essentially I can get a very high resolution solution with very high M and N without having to, blow up the memory of my computer like I could in a 2D problem. Okay, so with all that, we can actually define dynamic low rank approximation. So I'll have this reference at the end, but this is the seminal paper is by Otmar Cook and Christian Lubisch in 2007. And they're going to consider an autonomous ODE here, y dot equals f of y. And again, as I said before, this is just evaluating the dynamics of the operator f on a Riemannian manifold M sub r. So we're going to get into some geometry here, which is okay. So the primary principle technique, what you need is to know the tangent space. So unlike a subspace where the tangent space is the same as the subspace, in nonlinear manifolds, given for example, this curvature right here, each point on the space U, I borrowed this from other papers, so the notation's a bit different, but each point here, U, denotes a tangent plane or tangent space associated with that point. Of all essentially vectors that are tangent to this, with respect to the, in this case, we're using the Frobenius inner product for everything. That's so the tangent space is all vectors that are orthogonal to U, tangent to U, in the ambient space of n by n matrices. So we're going to denote that by TU of MR. And again, I want my low rank solution to always live in this manifold, to essentially follow this red line right here. So in order to guarantee that, a good way to guarantee that is to make sure that the time derivative of my low rank approximation lives in the tangent space at U. So I have this coupling between the time derivative and where it needs to live. Okay. So essentially, I want to maintain the dynamics of F though. And as you can see from this picture, if here's my current point U, the dynamics of F of U might take me off of that manifold. And that's mostly what's going to happen, right? You're not expecting to stay on the manifold. You're expecting to stay close to the manifold in terms of the dynamics. So how do I guarantee that the solution my approximation stays in the tangent in the low rank manifold? Well, I'm just going to essentially project the function F onto the tangent space at that point. And that's going to give it by a minimization argument, right? That's minimization argument between all functions in the tangent space at U and F of U minus Z. And again, I can easily represent this as a projection of a tangent projection operator. I'm not going to get into the specifics, but it's a subspace, so I can project onto it. And you can also write it in more of a weak Galerkin type formulation, where essentially the ODE U dot equals F of U is satisfied, but only tested against functions in the tangent space. So again, the nonlinear dynamics come from the fact that I have U is in two spaces. It's in F of U, and it's also in the tangent space as well, which creates some very crazy dynamics. All right, so that's the definition, and it's useful for theoretical results, but computationally, we can't use it, or we can't use it in its current form. And the reason for that is, again, I'm referring to U as an n by n matrix. I'm calling it a low rank matrix, and I'm making sure it lives in this manifold. But unless I have some sort of decomposition, I'm still, at the end of the day, it's an n by n matrix. So I don't need the evolution of U. I need the evolution of the factors of U. So since U is low rank, we can call it C times S times D transpose, and I want to evolve C, S, and D as a function of time now, as a system in C, S, and D that depends on time. And I can do this by explicitly characterizing the tangent space, this object that we created that's going to essentially map our dynamics to keep in the low rank manifold. And I want to do that in terms of the low rank vectors, not in terms of U, but in terms of C, S, and D. There's a lot of actually useful geometry in this, but the main thing to think of is, the main thing I want to say is that the space of orthogonal matrices is a manifold, and it's called the Stiefel manifold, and it's well known the tangent space of that operator, that manifold. I'm not going to get into specifics, but also this combined with the fact that we have a multiplication map that takes our low rank factors and gives us our matrix by multiplication. You can use these two ingredients to combine to give you the tangent space of the space of low rank matrices, by essentially a product rule formulation, as we'll see, but we can explicitly do this. So again, suppose U is rank R matrix and it has a decomposition where C and D are orthogonal and S is invertible, it's R by R. Then I can characterize a tangent space as the following variations in C, S, and D. And you can think of this as a product rule, right? I take the derivative with respect to C, that's my variation right here, fix the other two, take my variation in S, take the other two, the same, take my variation in D, take the other two. The only difference is that a standard product rule, you have these what are called gauge conditions to where S can be any sort of matrix. It doesn't have to be invertible. Delta S can be anything. But delta C is an n by R matrix that has to be orthogonal to C. And delta D is an n by R matrix that has to be orthogonal to D. The reason that these gauge conditions are placed is to guarantee unique decomposition of the tangent space. We want to have some uniqueness in how we represent objects in this tangent space. The reason, so these conditions come because if you look at the first two terms, if delta C didn't have this orthogonal condition, then I can essentially break up delta C into the components that are in the span and the components that are not orthogonal to the span. And the components that are in the span now have a choice. They can go into this space or they can go into this space now because these both have D as the span of the transpose. So without that gauge condition, you could essentially you can essentially make the representation of a single vector infinitely many things by just moving stuff from here to here or vice versa. But if you fix that, you get a unique decomposition. And moreover, if you have a function z that's in your tangent space and you say you have its n by n form, then you can represent the variations as the following algebraic formulations. And these should come by essentially algebraic manipulations. For example, if we want this bottom one right here, if I hit C on the left, C transpose on the left and D on the right, hitting C transpose on the left will kill this term because it's orthogonal. And C transpose C is identity, so these C's go away. And the same thing, if I hit D on this side, this goes away because delta D times D is 0, and this D goes away. So you're left with delta S equals C transpose CD.
Two quick questions. Why do you call them gauge conditions?
This is the notation they use in the paper. I think it's just
Okay.
I don't know why they call them specifically gauge, but it's the purpose of them.
Okay, I've just heard about gauge functions used in other contexts that come up in physics, so I was wondering if there were any relationships there. The second question is, I generally don't think of the SVD as a particularly unique decomposition. Is there something that gives you more uniqueness here than you'd expect in the standard SVD?
So we're not doing an SVD here, right? So so first off, S can be anything, just invertible. It doesn't have to be diagonal. The point is that given the factors of C, S, and D, given those factors fixed, we can then characterize the tangent space uniquely. So if I were to change the factors of the C, S, and D by putting a -1 right here and -1 on the C's, that could change how you represent vectors in the tangent space. But that's still, they're still, with respect to that space, unique. Okay. So with the proper characterization of the tangent space, we can then
Another
develop
question is this exact, or you have some truncation of the higher order terms?
So we're assuming here that U is a rank R. So we're completely off of the true solution Y. So we're just assuming we have a rank R matrix, and I want to know the higher tangent space. So to that, it's exact.
Yeah. Okay.
Okay. So now that remember my dynamical low rank approximation is defined by the projection of the dynamics onto the tangent space. But I'm gonna work with the Galerkin formulation because it's a little easier, I think, to work with. So now we can actually develop the equations of motion, which are the system of C, S, and D as a closed system of C, S, and D. Essentially, we can remove U from the equation entirely. To do this, you just choose particular test functions that isolate the variables you want to care about. So, for example, let's say I want to isolate the S variable. I want to have S dot equals blah. Then I need to choose particular functions in my tangent space. So to do that, again, Z is given by a generic element in the tangent space, and U by a product rule is given by this delta C, delta E, and delta S equals C dot S dot and U dot. So for the equation for S dot, we're going to choose delta C and delta D equals 0 to get rid of them entirely. And then we're just going to let delta S be a generic free variable W, where W is a generic R by R matrix. Then plugging that into the definition of Z gives us just essentially anything in the span of C and D transpose. And essentially then, if I plug these definitions into the equation right here, U dot Z, I can expand out U into my product rule formulation. And essentially the Frobenius inner product allows you to move C to the other side and D to the other side by taking transposes. This is the cyclic property of the trace. And what's notable is that C dot is orthogonal to C, so that goes away. And then D dot is orthogonal to D, so that goes away. So you're just left with the middle term of U dot. And then again, I can move the C over and the D over. And since C and D are orthogonal, they turn to identity, and I just get S dot times W. With the right-hand side, F of U times Z, or inner product with Z, I can move the C and the D over. And now, thanks to the equality right here, these are equal for any generic W, so therefore they're equal S matrix, R by R matrix. Because note the S dot and this are both R by R matrices, so since they're equal for every W, they have to be. So, and here I substituted U equals CSD just to show that this is now a close, this is the closed equation in CS and D. I'll do one more, just the C dot, the D dot's very similar. I don't want to, it's just a much more algebra. But essentially for C dot, I want to keep only the C part of the operator. So I'm going to choose delta C. Essentially, I'm going to take a generic M by R matrix. I'm going to project onto the span of D on the right, and I'm going to essentially project off the span of C on the left. So I'm going to do that by I minus CC transpose times W times S inverse. If I plug that into delta C for D and let delta S and delta D be 0, I will get this as my test function. So this essentially, again, takes a generic M by R matrix W, it projects onto the span of D, and it projects out to the span of C. And then you can follow the exact same algebraic steps. Now, again, instead of using C, I'm using the orthogonal complements. So therefore, it will preserve the C dot, and it will kill these two C's. So those go away. So I'm just left with the first term. And again, this is an identity operator on C dot. So, and I move that in D over, and I get C times S. Again, with f of U, I'm just going to move over the projections, and I get something that looks like this. And now that these equal for any M by RW, the first terms must equal, and I can just invert S, and I get an equation that looks like this. Again, a lot of tedious algebra, but it's just as simple as producing the proper functions to test and doing the algebraic manipulations. Again,
Can I ask quick
Sure.
question. I feel like I just don't know how to do the weak form stuff. How come you're able to just choose the delta C, delta D, however you want?
So the dynamic low rank approximation holds for any Z in the tangent space. So essentially, as long as I choose the delta C, delta D, and delta S, as long as they satisfy those gauge conditions, it's a member of the tangent space. So I'm essentially choosing only a select subset of the tangent space in order to isolate one of the variables. That's essentially what's going on.
And you've just chosen them carefully to make it work out. Yeah. Okay. All right. Thanks.
Yeah, the intuition of getting the special sauce is stare at it and figure out what you need. But once you have it, it's just a plug and play. D is the same way. I'm not going over it. You just flop C and D, and you get a F transpose here and a C inverse transpose here, or sorry, an S inverse transpose here. But it's the exact same thing, but slightly different. Okay, so once you have all that together, we've now closed the system, right? So before we had a U as the projection onto the tangent space of F, U dot, sorry, and now with an ansatz of CSD, I can then write this as a closed system in C times CS and D. So I can remove U from the equation entirely, and I can think of this as truly an update of the low rank factorization, to where my basis is changing in time and my coefficients S are changing in time. Now you might say, well, that's great, but this requires, I still need to have U, right, if I want to evaluate F. But this is where I say some structural properties of the ODE can happen. We'll get into this next time, but essentially, if your F treats treats how it evaluates in the M and the X and V space essentially independently, if those are have some separability between them, then you can evaluate these operators without having to build C times S times D equals U and then evaluate. You can essentially hit the equation with the D or the C here and compress it instantaneously with some algebraic manipulations. We'll see how that happens next week, but you don't have to actually go to the full M by N output in order to evaluate this. If your matrix, if you have none of those conditions though, then you would. So it's not a free lunch here. You have to specify problems that actually respect the structure of the low rank approximation. I also want to note that these equations are highly nonlinear, even though the right-hand side f could be a linear function, and that's precisely because the coupling of the tangent space characterization and what you're inputting into the function, right? You're coupling these, which can produce heavy nonlinear dynamics. Okay, so theoretically, how good is this? So this is straight from Ludwig's paper, just a quick theoretical result on how this actually does. So suppose you have your true solution y is given by some rank R approximation y sub r and some error term e. You could think of y sub r as an SVD. It doesn't have to be though, but you can think of it as the rank R truncation. And we're going to assume the following conditions. We're going to assume that the rank R truncation is uniform. The smallest single value is uniformly bounded above by rho. Sorry, bounded below by rho. We're going to assume that y is C1 essentially, and that the error is sufficiently small. This essentially gives you the error of the dynamical low rank. So choosing then the dynamic low rank initial condition equal to whatever the initial condition of your low rank is. So if you did an SVD truncation, that's what you would do here. You get the following estimate for the dynamical low rank solution error. So the difference between u and the rank R approximation y is essentially a constant factor of time spent plus the error in your error of your rank R approximation that you specified. So essentially you're as best twice as good, you're twice as worse than your SVD approximation essentially. But this only happens for a short time, and that time does depend on the singular value rho. So if your singular value is small, this estimate will break down after a short time. And all of this comes down to the fact that you don't know what your solution does at a long time. And it could theoretically, the rank of the true solution could dip below the rank you're at. And that the manifold of matrices of rank less than or equal to R, not fixed equal to R, is not a smooth manifold. And as your singular value degenerates to 0, the curvature of the manifold blows up. So you have you have some issues at that point. But you do have a nice theoretical result that gives you quasi-optimality.
Stefan,
Go
question.
ahead.
So in the previous slide, the condition on, is that a bound on E dot or on E?
That is on E dot, because we're assuming that essentially because we're assuming U0 is y sub r, the derivative bound will give you a bound on.
You assume it start from the low rank. The
Yes.
true solution is from the low rank, or?
Okay. Yes, the true solution starts from the low rank.
So you are not comparing to the true solution. You are comparing to the best, say, best SVD
Yes.
for every time.
Yes. Yeah. So yeah,
I
I mean, you do see more structural if you want to compare the other two, but this is the pros they used.
Okay, thanks.
One more quick question. I noticed that so once you have the derivatives of C, D, and T, how do you then evolve C, D, and T? Is it just addition, or is there some orthogonality condition imposed on each of the C and T factors that you need to take into account? Like how do you get from the derivative to the evolution of the factors?
Sure. So on a continuum, these equations preserve the orthogonality. You can show that if you hit C transpose here and hit C transpose there, you get 0. So you can essentially show that the norm of C doesn't change in time.
Oh, I see. Okay.
So if you start something that's orthogonal, that's you maintain that. How you actually evolve these equations is a whole nother topic, which is what we're going to postpone to next time. You really can't just say I'm going to throw a time step on these. Essentially, the curvature of the manifold comes in, and you can severely restrict the time step you can actually take to do a stable evaluation if you just throw a wrong or cut of 4 on this or something. But the talk potentially next time is how do you actually evaluate these? How do you actually evaluate these in terms of a numerical time stepping scheme?
I see. Thanks.
Okay, so I kind of want to give an illustrating example of the craziness that can happen here, just to give a full picture. So I'm going to do with a very simple problem here. it is just a simple relaxation to a fixed equilibrium. So time derivative of y plus, I should have put y dot, sorry. So y dot plus y equals gamma, where you have some fixed, some initial condition u naught, and your source here is fixed. It doesn't depend on time. Then you can easily show that the true solution is given by a integrating factor, whatever, but it's given by your initial condition goes away and you converge into the true equilibrium as time goes to infinity. We're going to suppose that both the initial condition and the equilibrium gamma are both rank 1. Then at most, this is rank 2. If these happen to have the same basis functions, then you would stay on a rank 1 object, but at most they can be rank 2. And we're going to consider applying, so again, very simple equation, have an explicit representation of the solution. We're going to try applying dynamical low rank with a small rank, because even though the solution is rank 2 at all time, you know, it's rank 1 at the beginning, rank 1 at the end. Can it capture the rank transition from 0 to 1? And we're gonna consider just a very prescribed choice of values here. So we're gonna let u be given by decompositions. U C0, S0, and D0, and gamma is given by C gamma, S gamma, and D gamma, where C is going to be some fixed alpha and beta at the beginning. We're going to make D the same thing for the initial conditions, and S is going to be 1. The equilibrium is going to have essentially alpha is 0 and beta is 1 for the basis functions, and we're actually going to make the coefficient -1. So if you can think of essentially alpha and beta being equal to 1, you can think of that as the upper half sphere on R2, and it's, you know, our initial condition lives somewhere over here, and our equilibrium lives below the lower half plane, you know, somewhere down here. Okay, since gamma is symmetric, you can actually show that C equals D, so we can ignore the C and D part, but we're going to parameterize in the same way as some alpha and beta, where S is some free variable. And again, because of the orthogonality conditions, alpha and beta equal 1. Alpha squared plus beta squared equals 1 for all time. And we're just going to assume that alpha can go, the x can go between -1 and 1, and beta can go between 0 and 1, some like polar sort of decomposition. Now, what's crazy is if you plug this representation into the equations of motion and do the algebra, you will get the following equations, differential equation system for alpha, beta, and S. And again, it's very highly nonlinear, even though this problem was very simple in the beginning. The differences between alpha and beta in terms of how they look is, again, because the equilibrium only has essentially the beta component highlighted here. So the alpha component disappears and it essentially doesn't matter. So you can, the alpha doesn't influence the evolution of B or S. So once you have B and S, you can create alpha. So we're going to decouple these two equations right here, which again, highly nonlinear terms in here for alpha. And again, I want to note that for S equals 0, you're essentially, when S equals 0, your matrix is 0, and that's not a rank 1 matrix. Again, dynamical low rank is defined on all matrices equal to 1. So the 0 matrix is not included in this set. So it's not defined. And that kind of lends to the fact that if I chose S equals 0, beta dot's not defined. And that's because of the fact that it has to be a rank 1 matrix in order to evolve this system in rank 1. So just to kind of illustrate what happens here, the below is the phase space plot for the two equations on the top right here and the beta S plane. So beta here is on the x-axis and S is on the y-axis here. So note that our equilibrium gamma is defined by beta equals 1, S equals -1. So it's down here in the lower right corner. And it is a locally attracting equilibrium. If I start near, pretty near the equilibrium, no matter where I am over here, as you can see, the dynamics eventually be there for a long time. Again, there might be error in the dynamical low rank approximation, but in terms of actually capturing the equilibrium behavior, we do hit that, as over here. What's interesting, though, is if I start with an S positive here and beta not equal to 1, then the dynamics actually don't take me anywhere near the equilibrium. They actually take me down to 0. So even though it's I can fully see gamma in the operator, and one of the dynamics to try to do it, the dynamics combined with the representation are going to force my equilibrium, or force my low rank approximation to converge to the wrong solution. As something wrong as n equals 0. Sorry, as time goes to infinity. And it can't cross, and the dynamics get very crazy when s is equal to near 0 because it's -1, and it actually pushes me way farther off. If I started just below it, I'll get down to it. So we have some very odd behavior around essentially the point where you degenerate off of the low rank manifold. If s is positive and beta is exactly 1, so you're on this line right here, then actually you can avoid this all entirely, and you will just time step down to the proper equilibrium and avoid this odd feature discontinuity here. Now, again, numerically, you're never actually equal to something. So if you're just a little far off, if you're just a little, if your error is a little off in your initial approximation, then boom, you're heading down over here. Lastly, if your beta is 0 right here, then you have no hope of ever maintaining coming off of this manifold over here. You will converge to 0. And that's because, again, I'm going to go back here to, if beta is 0, then your initial basis is completely orthogonal to the equilibrium basis, and you will never actually see this gamma when you hit with C and D. They'll just disappear. So you're going to essentially act like gamma's removed. You're going to act like you're evaluating this ODE, which is going to take you straight to 0. So again, depending on where you start, and you can get very different results in long time for dynamical low rank. I want to say that even if you do these techniques that I'm going to talk about next time, which remove the necessities of the curvature and all this, that allow you to take much larger time steps, stuff like this still happens. If you actually do these time discretization techniques, what will happen is you will follow the dynamic exactly here. You will start converging to 0 until your solution is sufficiently small to where it is smaller than the time step in norm. The singular value is smaller than the time step. Then the time stepping error actually allows you to jump over this line. And then once you're in this regime, it'll then take you to the correct equilibrium. But instead of going in the straight path like you want, you will converge down to 0 until it's sufficiently small. You'll jump over and then converge over to the correct equilibrium. But that's a bug, not a feature of the method. The fact that you're so small that the time step allows you to make consistency or jump over this highly nonlinear line s equals 0. It happens that way. So again, just to illustrate that some very weird dynamics can happen here. You're not expected to see these. You're not going to, this is a very contrived problem with very specific parameters to make this happen. I've never seen this stuff happen in practice. Normally, you choose some rank to give you some padding, which allows you to kind of phase out these effects. But if you were to follow the equations exactly, you can get some very interesting stuff. Was there any questions on this before I continue? Okay, so we're going to finish here briefly. So I want to comment that you can extend what all I've talked about to the domain of tensors as well. Some multilinear rank tensors, script y, which are I1 to ID in each dimension. You would think that the canonical representation to extend this into the tensor format is to do a Tucker decomposition. Think of it as the generalization of the SVD in a sense, where I have some core tensor S that's low rank, and I have some factor matrices U. And then you can essentially repeat all this just like we did for the equations of motion for the low rank matrix case to the Tucker tensor case, where you have a D+1 in systems of equations of motion where S inverse is replaced with a pseudo inverse of the in-modal unfolding of the tensor S. I will also note, so that's in this paper right here. I'll also note that later they did reformulation of the dynamic low rank in both hierarchical Tucker formats and tensor train or matrix product state formats. So while not as clean as the Tucker case, they do exist if you want to look those up. So lastly, I want to kind of prelude into the curvature prelude in the talk 2 weeks from now. And essentially is that we talked about how do you actually evolve these equations of motion. The issue again is that these are numerically unstable to time step unless the time step you use on whatever method you do, implicit, explicit, whatever, is smaller than the smallest singular value of S. And this has to do, again, it's not a time step constraint. It's not a problem constraint. It's a manifold constraint. The manifold can have very high curvature when the singular value is small. And you have to think, if I'm going to naively just follow the dynamics of this manifold, I need to, when it starts curving very sharply here, I need to lower my time step in order to capture that curvature exactly. And that's essentially what it's doing here. Now, again, this feature, this ability right here happens quite frequently, because if you over approximate, say you have a rank 5 solution, that you know your solution is close to rank 5, and let's say you use rank 7 to approximate to really make sure you get it correctly. Now your smallest two values, singular values, are near machine epsilon, and you pretty much ruined your time step restriction. So the next time we're going to talk about some numerical integrators to avoid this issue. And to give a little hint, you can think of this manifold as what's called a ruled surface. So if you had a cylinder with two ends, and you can imagine a string attached, then this manifold right here, essentially you're taking that cylinder and twisting it, each on counterclockwise and clockwise respectively, to where the strings now meet at the center and create a very high curvature object. But each of those individual strings is straight. So essentially, instead of trying to follow the curvature of the manifold, what you can do is use some operator splitting techniques to follow a straight line for a little bit and create some consistency error, but avoid the curvature of the manifold, therefore bypassing this delta T restriction. Because each one of these straight lines is essentially an embedded subspace in this by usually fixing one of the coefficients in the approximation. So if you do that, you can follow these lines, and that avoids the curvature aspect, and you can evolve the dynamics and with the sacrifice of consistency error in a more stable format. And we'll talk about that next time. So here are the sources that I gave throughout the talk if you want to see them, and I'll take any questions.
I have a question, just the previous slide, in terms of time step constraint. So you said that you are going to talk about the integrator next time. I'm just curious, do people use incorporate implicit or at least a semi-implicit way to do this?
To do the integrators we're going to talk about next time?
That's right.
There's the field is wide open. I mean, it's only like 10 years old regardless, but a lot of the techniques we're going to talk about are based on implicit type methods. People have done implicit type work as well. I've actually done some implicit type work. It is difficult to do. It's hard to do implicit problems because these integrators essentially decouple the tangent space from the evolution of the operator. And the problem is, if you time step too far, you can be very far away from where the dynamics are where the manifold is trying to take you. And if you want to try to converge that, you can create some very large errors that might not actually converge. And I've done some work where you take problems and you'll try to find a fixed point solution, some map you create that will give you the proper value, and you'll just oscillate because essentially the curvature is bouncing you in between 2 points that are both equally valid. So it's wide open.
Because potentially you can think about this curvature could be, as going to infinitely small or infinite large, however you say it. Mm-hmm. Then your integral, whatever the integrator will blow up, right?
So yeah, if you were to try to do these in that regime with a larger time step, yes. But if you decouple, right? If you decouple, you can at least pose the problem. It's conversion that's the issue. Because right, if you have a very high curvature, you can think of if this is your minimum you want, you just bounce in between here, right? You don't.
Yeah.
Exactly.
Okay.
Any other questions? This has been very helpful to me. Okay, if there are no more questions, I will basically stop the recording, or maybe I don't need to do it. It will stop by itself. Here it is.